Good morning and good afternoon, everyone. Welcome back to Mr. Sniffin's geometry class. Today we are going to be discussing our compass. You might have saw last week we were using a slightly different compass, one from last school year. Today we're going to cover our new compasses which just arrived and which most of you should have in your possession already. If you haven't gotten a compass yet, just as a reminder, please fill out that form from last week. But besides that, I want to go over some of the variations that we'll see here in this new compass, how we're going to be using it. I'm also going to cover some of the material briefly from last week, so we have a good model with this newer version compass, and then we're going to try out a couple things associated with our transformations. So first off, with this compass, as you know, it's a little bit different than what was previously seen, but all compasses in general work in the same fashion. You have a location from which you're going to align your rotation from, and from there you have a certain length that you're going to use. This length is what we use to stay consistent in our movements. What's nice about our new compass, though, is a couple things here. We have a nice flat straight edge. We have a right angle in the corner, nice and perpendicular, which on both sides, which is kind of cool that we can almost, in a sense, understand if we are perpendicular with something because we can just line our two 90-degree corners up there and then just plot our successive point using this guy right here in the center. So long as our corners are aligned properly, making that linear pair, that nice line, wherever this circle, wherever this whole marker is going to be nice and perpendicular. In addition to that, the way that we're going to go about managing everything today, what we'll see is here in the center of our piece, might be able to see it here, there's a little X in the center. In that X, exactly where it crosses is where you're going to want to hold your finger down on various points, for instance. That's going to be that center point, that center of rotation from where we're going to move through. So you need to, desperately need to get that as line as accurate as you can in the center. As a reminder, we're not engineers, so if we make slight little tiny various mistakes, we can see if something's pretty close, but in general, you want to be as accurate as possible. So, some things to take in consideration. Besides aligning your point nice and squarely in the center, we have to take in consideration these marking holes here. Each hole, the same exact size. Each hole is going to represent kind of just where we're going to be of distance from. So if we're, say, 5 centimeters away, we have a 5 centimeter circle, we're going to pop it in here. One thing that you'll notice, though, is when you put your pencil point in this hole, the pencil point itself is considerably smaller than the hole. What that's going to end up doing is when you're making your movements, and I'll show you here, it's not picture perfect. You have variability in where that point is. So try and stay consistent in terms of when you're doing your movements, like if you're going to be pushing to the inside to the left, inside to the right, because you'll end up being, say, slightly off. There is distance in between those 2 points. So while that is relatively small, we're talking about, a couple millimeters in terms of length. If we're doing huge arcs where we're trying to exactly copy patterns, you might make a mistake. So I'll explain how we're going to avoid that as we go through here. Okay. So let's get started with our refresher from last week. We spoke about how to copy an angle and how to copy a segment. Copying a segment is super fast, super simple, almost identical to if we were just to take a ruler on something, measure it out, and then just slide it over and replot it out. What we're going to do with our compass is put that center point here, our rotational center point, right on the beginning of our segment. We're then going to take our slidey piece and we're going to try and get the end of that segment directly into the middle of that hole. Try and do it the best you can. you can kind of feel, if you push the center point down, you could kind of feel the slight notches that are there that go back and forth, so you can get it aligned. It does slide to the center point, but I would just hold that piece down. Get it nice and aligned wherever you are. However long you draw your segment for this example doesn't really matter. But we're going to take that value. That value basically, what we're going to do here is plot out our starting point for our new segment. Got our A prime, and post it out. Line up, and wherever this arc is here is going to be equidistant. It's all going to be that same length of A, B that we found up here. All these different points here are all that same. You can kind of see the arc in the camera there. So we can just pick any arbitrary point we want. You say that's B. Go through, we find it, we plot it out, bam, we got our new segment. Copy an angle itself, it's not too hard. It's just a couple steps. But this is where we start to see like this idea of like Euclid and all these other mathematicians and engineers at the time are so smart, so like such geniuses in terms of how they came up with these methods. I'd like to show you this first one here. What we're going to do is we have an angle. You can draw it however you like. Flat straight line, parallel with the bottom of your paper makes it a little bit easier to see. Plot out your additional ray wherever you want. And what we're going to do is just create an arbitrary ray just somewhere else on the piece of paper. So we got a nice long ray here. I'm gonna make this segment just as long as the angle above, just to kind of show how accurate we are. Another thing to consider is while you're thinking about where you're going to put that centerpiece, if you draw a big huge circle, it's going to be harder to kind of get it into the middle. So you want something nice and small, but something visible enough that you can see through here. Alright, so first thing we're going to do is we're going to go up to the original figure, which we'll just call, say, angle A. We're going to go ahead and find a spot wherever we want. We're going to do a nice little mark down here. Since I'm using line paper, I'm going to just use my grid to help me out. But I'm going to draw an arc from that location, this arbitrary section I'm going to pick. Make my arc. Come up here, plot it out, hit my intersection there. I'm going to go ahead and label this point B and point C. I'm going to go down here. Come up. Arc all the way through. Give ourselves a little bit extra. What we're trying to basically do is land somewhere around here in a similar fashion. The way that we get this point C is we have our B. We know B is exactly this far. We kind of, just measured that out. But how do we know where point C is? We can go ahead and say, just measure down here and go, okay, I'm going to just put point C here, but you'll see that circle, if you will, it kind of just continuously overlaps it. So we have to triangulate in a sense. Triangulation is when we're using 3 points to kind of get our location, because we have 3 reference areas or 3 portions of proximity. You might learn from like some cheesy show like 24 or CSI with cell phone antennas. But here what we're going to do is find the distance between B and our intersection at C. Since my angle is 45 degrees, or sorry, close to 45, those values are pretty similar, but I have to make a little adjustment here. So I got my new measurement. I'm finding exactly where I am on point B, lining it up with my new marking. I'm now going to go down here, my A prime, my B prime. I'm going to go from B prime with my new measurement, and I'm going to make an arc related to where those two lines intersect. So it looks about the same. We can kind of see this box here. Intersection looks almost identical. I do know as a reference, since I'm using a lined paper, that I'm going to be around here. My intersection should go through. But if I line it up here, and remember you're leaving space for your pencil tip, we're going to go from A through our intersection. All right, and it looks like we're pretty good here. Extend out pretty far. Our angles should look pretty much identical. One of our compare and contrast methods we can do is use that slope formula. 1, 2, 3, 4, say 4.5, and we're at about 2.5, and we go up 1, 2, 3, 4, 4.5, 2.5, and we're about the same exact spot. Another thing that we can do is using that original line that was drawn, we can transpose that and see where the intersection occurs as well too. Then we're, repeating the process over and over again. But this is how our ancient or early history friends used to kind of reproduce these values when they didn't have consistent systems of measurement. They would use their compass. Obviously looking a little bit different than this. One of those more traditional triangular types where you have, like a pencil on one end, a metal point on the other, and they would use that and turn that itself like a wedge. Yeah, so let's go look at some other stuff here in terms of our material. That was copying a segment, copying an angle. What we're going to do right now, once again, is our perpendicular section. In terms of creating perpendicular lines, process not too hard. We're going to keep this idea of equidistance or equal distance as an important factor. Okay, so we're going to create a perpendicular bisector. To do this, we're going to create just a line. Anywhere in your paper, doesn't matter the length. So this line here has about a length of, say, 10 boxes. The way that we can figure out the midpoint just automatically here is we would count our whole length of 10 divided by 2, and that would give us our midpoint. Also have our midpoint formula we can use, like set up a whole grid, label out our points, and that's x1 plus x2 divided by 2, comma, y1 plus y2 divided by 2. Or we take our length of 10, since we have a flat line, divide it by 2, and we get about 5. 1, 2, 3, 4, 5. So I know this location right here is my midpoint. So when we go ahead and do our perpendicular bisector, we should get a line that's going to go straight down here, forming that 90-degree angle. But the way that we go about doing this using a compass, say, is we need to find a place That's about say 3/4 of the way down our segment. So somewhere around here. And what we're going to do is basically draw an arc on the top, an arc on the bottom. We're going to use that same distance, arc on the bottom, arc on the top. So we're going to use this idea of equidistant arcs to try and figure out where our middle is. Mark up here. I'm going to use my graphing paper kind of as a guide. I know my intersection is up here, so to keep my paper nice, what I'm going to do is draw my arc near that intersection. Once on the bottom, once on the top. And you'll see because of that circle here being slightly large, when you move your pencil back and forth, you're going to end up getting a little misalignments there. So you want to be kind of consistent. So one suggestion here is go backwards and then forward. So your pencil should be locked in kind of position, come across, intersect. And what we should have here, if we did it perfect, is our intersections should be aligned right along the top and bottom. I'll show you here. My little copy, a little bit off, but we can imagine if we do it again, say we find slightly different marks. Oh, and as a reminder, last week I posted up all the directions, paper-based directions for you. So if we're going too fast in the video, you can always stop and go backwards. But here you want to make sure that you have your alignment on the bottom, on your circle there. You want to have your consistent measurement. Just redo it and you see it's a little bit better. It's like literally right perfect as we go through there. So what we end up doing is because we have this equal distance, we have this system. Evenly spaced, evenly spaced, evenly, evenly, evenly. To connect all those even points ends up being done so with a perpendicular line, which is pretty cool. So we can say this right here, 90 degrees. If we labeled everything out, we can say that segment AN is equal distance or congruent to MB. If we start like labeling other things as well too here, like if we had E and F, MF would be congruent to ME. These are going to be different. AM and MB are going to be different lengths. But this is how we start to create different systems. As we expand throughout the school year, we can take this idea, make it a little bit more detailed, and then go ahead and create like squares and other various shapes through this methodology of perpendicular lines as well too. But the lesson that we're going to look at for today is going to be related to our current unit being transformations. We're going to take this idea and expand upon it a little bit more. So first thing that we're going to practice out right now is going to be doing lines of reflections. So to do a line of reflection, which you saw in our notes from Monday and the previous week, a line of reflection allows us to take a value and plot it evenly across an arbitrary line and plot it on the other side with that same distance. So I'm just going to take some random points here. So say we have segment PR. If we wanted to go ahead and plot segment PR across our line of reflection, we'll say this is line X is equal to, 10 or what have you. We know from class all we have to do is go in a perpendicular fashion to our line of reflection and plot that same distance. We can go ahead and say like 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, and that would be plotting point R prime. Our new point, would be reflected across our line X is equal to 10. But if we wanted to use old school compass style, we're going to kind of do this perpendicular idea again. We saw in our previous page, perpendicular, when we were creating that, we have those equal lengths. We're basically going to do this idea sideways and plot it on our paper for our reflection. So I'm going to go to P here. I need to find a length that allows me to get to my line of reflection and a little bit past. I like when I'm using my compass, personally, I find to do the larger movements more accurately. I feel like with the small ones, if I'm slightly off, that value gets exaggerated more. Being off by a millimeter when you're talking about just a centimeter, you're off by 1%. If you're talking about a kilometer, you're talking something super small. So I'm going to pick my value here. And I am going to make an arc through my line of reflection on both sides. Got to extend this one down here. So what we should have now is from point P, make sure not to mess up your measurement, but from point P, we have our arc. We have two equidistant points. What we're going to do now is from point P, I'm going to do that same big looping arc. I already know that we're supposed to hit here. So I stop my pencil not too far after it. Go to my other intersection along my segment. Alright. Looking about right. If I just count it out here, we should be at about 9. 1, 2, 3, 4, 6, 7, 8, 9 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces. Awesome. So I can actually go ahead, plot here. We have point P prime. Connect our figures. Bada bing, bada boom. And we got the same exact segment. If we want to check to see if reflections are technically isometric in that they do not change congruency or they do not change size, we can go ahead and use our distance formula that d is equal to radical x2 minus x1 close parentheses squared plus y2 minus y1 close parentheses squared. We can use that equation. We can do our slope. If we have identical slopes without having to reduce our fraction, we have the same exact value as well too. All right, let's take a look at our last construction for today. We're going to be looking at creating parallel lines with line paper. That's relatively easy since we have essentially our slope. What we've been doing in math class for years. We can use slopes or identical slopes to kind of plot points, connect them, and create parallel lines. But as we learned last week, our graphing system that we have here, Cartesian graphing system, we're talking about 1500s, 1600s for popularity, and obviously Euclid didn't have this type of stuff. So what they were able to do is use this system of equidistant arcs to kind of recreate those angle problems like we saw before, but then do so in a manner where we're duplicating the angle on top of each other, aka like creating parallel lines. What we're going to do right now is to start off, we're going to go most of the way down our page here. I'm going to create a nice little line, nice little ray. Label my point here. We got point A. I'm going to go ahead and just create a random line. This line doesn't need a specific slope or anything like that. This is just going to help us plot our parallel line. I have a relative marking to use against. So I'm going to go from point A. I'm going to find a random distance here. So I'm going to use that convenient outlined paper to kind of just spot an intersection. Try and get my everything nice and even. So from here, I'm going to make an arc. This location right here, I'm going to call point B. And we have point C. Alright, so now we have created a system of length associated with segment AB. As we saw in our previous example, to copy our angle, we need to triangulate. We need to get all of our values. So from point C, we're going to plot out our B value. And notice how we're plotting it along this line versus the other one. We're going to go from up here, from point B, we're going to come down and swoop. And we're going to stop kind of relative to where we think that parallel line intersection is going to be. Since we're using a line paper, it should be somewhere around here. And now what we're going to do is kind of like our angle, we're going to go and find the distance between B and C now. So that distance for B and C, we're going to make sure everything's lined up nice and evenly. Plot our points. I'm going to go up to here. And this is where if you at this intersection, potentially making it a little bit bolder to see through the compass, but you gotta, still maintain, get it right in the middle. So I'm going to take my compass, I'm going to put that markings location close so I don't have a big huge arc. I'm going to give myself a little bit of distance, make sure my pencil's straight. Boom, we got our intersection. Our intersection's right along our line. And now we can plot. So now we have two parallel lines. So a few things to take in consideration when doing parallel lines. This is when it starts to become a problem where things are slightly off. So when we're talking about angles, we're talking about like dividing a circle into 360 pieces, or at least 360. They're relatively small. So if we're off by a little bit over here, a little bit over there, there's going to be some variation. For instance, here you can kind of see on the paper, my pencil point starts above my circle versus in the middle. So by the time I get to my intersection, just, a few centimeters over, we can already see my line over here starting to trail down. So that's when we're talking about staying consistent. If we're worried about grades, things like that, it's another discussion. On the Regents on the New York State exam, you're supposed to have the correct arcs, the correct line measurements, like in terms of the correct system done properly. So if you end up, measuring it out, but then you're off by like a little tiny bit, it's okay because I know that you used the correct method through these markings. But yeah, constructions are fun. use these to then go ahead and start dicing up things, toss in some perpendicular lines, form another one, toss another perpendicular line and go 45 degrees, things like that. And you can get some pretty cool designs. You'll notice a lot of the lessons shared in class have geometric designs in them. Those are mostly hand-drawn. Not for myself. I have some if you want to take a look at it, but go online, type in geometric designs or compass drawings, and you'll find a lot of cool stuff, especially on YouTube, lots of how-tos as well. But I hope you liked this lesson. If you have questions regarding the material, once again, there are step-by-step written instructions on Google Classroom you can use, and that'll help you out as well. Hopefully the constructions will also help you understand kind of the idea of transformations, translations, and reflections, and all that as well too. But until we see each other again, have a nice day, stay safe, wear a mask. Definitely wear a mask. COVID's at its highest rate in the US, so stay safe. Bye.